Hello, everyone. Glad to be back to the stage, and I'm very excited to introduce our next talk, Jailbreak Apple iOS16, defeating code signing using a PPL exploit. And so iPhone jailbreak is a kind of cannot miss topic at any security conference, and for very good reasons. It is incredibly challenging. Apple iOS has been evolving over the years and becoming increasingly insecure. But as hackers say, where there's a will, there's a way. So to be honest, I used to be a frequent speaker for such a topic, but now we have young talents at GEEKCON. Please join me in welcoming Lars from Cellebrite. He will be diving deep into the magical techniques used to jailbreak iPhone 16. Give him a wave of applause.
Hi, so not iPhone 16, but iOS 16. I'm Lars. I'm employed at Cellebrite, and in my free time I work on jailbreaks. I mainly make these for my own because I want to have a jailbroken device and have control over my device. And today I'm going to show the code sign bypass technique that's used in my jailbreak, which is called dopamine. Yeah, that's basically what I just said. I got into this in 2022. Released Troll Store, which is like an app that allows you to install unsigned apps. And then I worked on dopamine, and I recently also updated it for iOS 16. So everything I will talk about here also works on iOS 16. Yeah, so first let's discuss some motivations. So a code signing bypass is basically the integral component of a jailbreak. And previously in the past, this was done using kernel patches, but that broke because of KTR, which I will talk about later. And then for some amount of time, jailbreaks were using detached signatures and an AMFA-ID patch. This was until iOS 15, and basically Apple introduced a new feature called PMAP-CS, which makes code signing be behind PPL now, which is also something I will discuss soon. But yeah, so our goal today is to make it, to modify the system in a way so any binary can execute, whether it's like signed by Apple or not. Yeah, so let's discuss some basics. Yeah, so the stuff that makes jailbreaking hard nowadays is are post-exploit mitigations. So you have a kernel exploit, you have kernel read-write, and you still have some parts of the system that you cannot touch. So the most prominent one is KTR, which essentially protects any kernel text completely. So it's locked down on a hardware level, you cannot write to it at all. And it's used on constant stuff that only has to be written once, and then it can be locked down. Then you have PPL, which is similar, but it's for volatile data. So there's essentially an additional layer on top of the kernel which protects some data that Apple considers to be like important for code signing and stuff like that. And there's also a kernel PAC, which provides control flow integrity, and additionally also some cryptographic signatures are used to protect important data. And as an attacker, you cannot fetch like these keys and cannot sign stuff yourself. So there's a quick overview of the kernel memory. So on the one hand, you have like stuff that is only read or only read an executable. This is protected by KTR. And then on the right side, you have stuff that is, damn, that's barely readable, but yeah. You have volatile data, which is also written to at runtime. And there some of the stuff is completely unprotected. Some is protected by kernel PAC, and some is protected by PPL. So let's go through some assumptions that we make. So all I will talk about here assumes you already have a kernel exploit and a PPL bypass. For this, we are going to use the operation triangulation PPL bypass that Boris will also present tomorrow, I think. So yeah, so basically we assume we have already completed exploitation and our app has PPL read-write. Notably, we do not have a PUC bypass for iOS 16. So we do not have the ability to override stuff that's protected by the cryptographic signatures of PUC. And we also don't have the kcall primitive, which means we cannot influence the kernel code flow in any way. We cannot arbitrarily call kernel functions. And now the question is, with just the PPL bypass, how can we use it to bypass code signing? So let's discuss some primitives. So basically, in jailbreaks, the most important thing that you will need to have is nowadays in modern jailbreaks, like some handoff. So in this case, it's PPL read-write handoff. Handoff refers to being able to have PPL write primitive in one process and giving it to another. And in practice, we will achieve this by modifying page tables. So also basically the idea is we have some jailbreak server that gets started during the initial jailbreaking, and we then pass the PPL read-write primitives to it, and then this server can provide functionality to the rest of the system as it requests it. Yeah, and also during the initial jailbreak, we also hand off PPL read-write to ourselves from the exploit primitive just to gain stable PPL read-write, basically. So let's first discuss memory management on a surface level. So essentially, in memory management, you have the distinction between physical addresses and virtual addresses. So the page table is essentially what maps certain physical addresses to virtual addresses, and the PMAP layer is what manages page tables on Apple operating systems, and the PMAP layer is basically the layer to interact with physical addresses, and the VM layer is some component that allows interaction with virtual addresses, and it also like calls out to the PMAP layer as needed. And both the kernel and the userland processes will call into the VM layer. So for example, when a userland process calls malloc, it will go through the VM layer. Yeah, and that's basically how it works. So we will start at the bottom. So at the bottom we have page tables. So this is what the MMU of the processor will use at runtime to translate a virtual address to a physical address. So the kernel and every single process on the system will have such a page table. And essentially, the page table consists of a way of having like a contiguous address space, in this case hex 0 to like hex 8 billion. And so the level 1 page table is essentially a constant sized page table that covers this address range. And as needed, you can also have level 2 and level 3 page tables, which are external. So the entry of the parent page table will point to it. And basically these child page tables provide more granular control over every page. So if you have level 3 page tables, you can truly control every single page and what physical page it is mapped to. So on iOS or in the kernel in general, every single mapping will be done through a level 3 page table. And this will be important later because if you see it, like the level 2 and level 3 page tables are allocated, so they are allocated at runtime. And if we, for example, want to create an arbitrary mapping of some sort, we need to be able to allocate those page tables ourselves. Yeah. So let's discuss the PMAP layer. So the PMAP layer essentially is a layer to interact with physical pages. And on RM64E, as explained, it's covered, it's entirely in PPL. So all structures related to it are protected by PPL, and without a PPL bypass, you cannot interact with them or override stuff. But we have a PPL bypass, so for this talk, it's not that relevant. Yeah, and as I explained, the MMU will use the page table that the PMAP layer manages at runtime to translate addresses. So one thing that's important is that every single physical page that the kernel recites has a descriptor. So there's a global array which is in some variable, and it contains a descriptor for every single page. And in there, it is tracked what kind of thing this page is used for. One thing that is important to us is the last one, which is the PMAP type PD, which indicates that the page is used as a page table. This is important because later we will want to allocate a page table. And in order to do that, we need this specific type, because if the page table we use doesn't have this type assigned to it, it will basically panic the system when the process exits, because the system will try to free the page table and it will have the wrong type, and then it will panic. There's also more attributes depending on the type, but not relevant for now. Well, and there's also the VM layer, as I explained. It allows kernel and the user land to interact with virtual addresses. Yeah, so here's a quick example of how the VM layer and the PMAP layer interact. So for example, in the user land, you would have code to do an allocation. In this case, an allocation of one page. And in the kernel, it would call VM allocate and VM map enter. And at this point in time, this memory doesn't actually exist. It just creates like an entry in the VM layer to say, at this page, there's memory. And then only when you actually access the memory you allocated, it will trigger a user abort or like a data abort in the kernel. And then this will call out to VM fault. And that will then call to the PMAP layer to actually assign a physical page to this virtual address. And then it will rerun the instruction that triggered this abort, and then it will actually perform the write. So as our end goal is to inject page table entries, we want to do this so we can map arbitrary memory into the process, and from there basically use it as a means of doing a complete physical read-write. Yeah, so we need to be able to allocate level 2 and level 3 page tables, as I mentioned. And if we don't do this, again, the system will panic. Yeah, and something additional to keep in mind is when we inject the page table entry, we need to avoid the address range that is covered by the VM layer, because if we don't, then the VM layer might overwrite or somehow destroy our mapping or panic the system if it tries to do so. So we essentially need to keep our page table entries to some unused area of memory. So as we can see here, the VM layer only covers a small amount of a processor's address space. So the PMAP layer, like the full address space, is much bigger. So essentially what we need to do is when we inject a page table entry, we just need to avoid that small part that is covered by the VM layer, and everything will be fine. Because everything that the VM layer doesn't cover is essentially completely unused. Okay, so how do we actually allocate a page table? So as I explained, every single page has a descriptor in some global list, and this global list contains a descriptor for every page. Yeah, and as you can see, basically every page has such a PT descriptor, and that has like some general properties of it. For example, the PMAP or the virtual address it represents. But it also contains a reference to the PTD info, and this PTD info has a ref count. And when we talk about allocating a page table, we essentially mean we leak one from the system, and then we reuse it for our own purposes. Okay, so to leak a page table, we can trigger the system to allocate a page table inside our own process by just allocating like the address range that one level 2 page table covers in userland, and we need to also align it by that value. So if we do it, we can do this to POSIX memoline, and the address we get essentially then is one entire level 2 page table. And the important part is that we can trigger the deallocation of this when we want by just freeing this allocation again. So what we can do now is we can just cause the system to leak this page table by finding it in kernel memory and arbitrarily bumping up the ref count variable. And when we do this and then we free the allocation again, it will free the allocation, but it will not free the page table because we bumped the ref count. Afterwards, we can decrease the ref count again, and we have now a leaked page table. It is unfortunately still associated with the process, so we cannot use it for another process easily. So we need to figure out a way to do that as well. But the more bad problem is that this page table also is within the VM layer. So very easy solution, we simply find the descriptor again, and inside this descriptor we can simply replace the PMAP and the virtual address with the object of the process and the virtual address we want. So after we've done this, we can essentially assign this page table to any process at any virtual address we want, and this will prevent the system from panicking. Yeah, and basically we can now leverage this to gain proper physical read-write. We do this by simply mapping in the entire kernel physical address space. So in the kernel there's like gphys size and gphys start. These are global variables that contain the information of where the physical address space starts and how big it is. And after we've used the techniques shown in the past slides, we can simply build a function that simply allows us to map one page to one address inside our own process. And now we can simply enumerate all possible pages and map them to some area inside our own process. In practice, I use the address hex 70000, which is the last level 1 entry. And you can simply map the entire address space plus that value, and then you essentially get access to the entire physical address space of the kernel in user space by simply taking the pointer and adding this value to it, and then you can just dereference it. And this is also the fastest possible way of doing kernel read-write. So here's like a small illustration of how it looks like. So you have the VM layer at the top of the process, and then we have this physical read-write mapping at the end of the process, and this covers the entire kernel physical address space as seen on the right. And yeah, this allows us to just read kernel memory as user memory. So if we want to do kernel virtual read-write, we can also do that. We simply need to read the kernel page table and do address translation ourselves, and then just do physical read-write. So with this primitive, we have basically everything we need. So all we need to really do now is figure out how to use it to bypass code signing system-wide. So here's a small illustration of how code signing works on iOS. So the key part here is that the first two things that can make a binary actually execute, so in terms of code signing, are the static trust cache and the loaded trust cache. These are essentially objects in the kernel memory that contain hashes of binaries that are allowed to be executed. This is in practice done for the binaries shipped by the operating system as part of the static trust cache. But there's also a mechanism that allows Xcode to mount additional images, and for the binaries on these additional images to execute, Xcode will trigger a loaded trust cache to be loaded. So this is cryptographically signed by Apple. So we cannot directly just load any trust cache we want. But as the trust cache in memory is only protected by PPL, what we can do is we can simply, with PPL read-write, allocate some memory and just treat it as a trust cache, write the hashes we want into it, and then add it to this linked list of loaded trust caches. And when we do this, this allows the binary to run. But the problem is, like, it's a manual process right now, and in the end, we want to be able to have it completely automated for any binary. And this is what we will look into now. So initially, what we do is the jailbreak bundles some binary folder with a bunch of binaries it uses, and it then injects a trust cache with the hashes of those binaries. And this allows us to go from just PPL read-write to be able to execute arbitrary code as user space or with arbitrary entitlements, basically. And again, we want to get to the point where any binary can run and not just stuff we injected ourselves. So we need to automate this adding of a CD hash to the trust cache somehow. Yeah, so basically all binaries running in user space are spawned by POSIX spawn. And there's also a few other processes, functions like execve and something, and there's also libraries which are also important. But for the simplicity of this presentation, I will focus solely on POSIX spawn. So normally you pass a path to POSIX spawn. This will call out to the kernel, and in the end it will like spawn a process. So the idea is, if we can hook POSIX spawn inside every process, we could automate the adding of the binary it's supposed to spawn to trust cache and then call the original implementation. This is what we will do. And to start off, we will target the launch-D process, because this is essentially the root process of the userland, and it spawns all other processes. So when we hook launch-D, we can go from there to the other processes later. And to do this, we can simply, when we have already arbitrary code execution or with arbitrary entitlements using manual injection, we can have one binary obtain a task port to launch-D. And then it can spawn a thread that calls DL-open on some library. And as long as this library is in trust cache, it can inject into launch-D. And then we get code execution inside launch-D. And we can hook POSIX spawn there to start out with. And now inside this POSIX spawn hook, we can bypass code sending essentially. But we would now need to extend this POSIX spawn hook to the entire system. So also inside launch-D, we will have a jailbreak server implementation that basically intercepts XPC communication inside it and allows any other process to make requests to it. And yeah, what we also do is we inject this library inside launch-D, and then we do a physical read-write handoff to launch-D. So launch-D now has our code running, and it has physical read-write, including writes to PPL pages. And now we can essentially add an API call inside launch-D to add some executable to trust cache. But now that we have this API, we still need to make the rest of the system use it. And for this, we use a system-wide hook. So the idea is we have one library that hooks POSIX spawn, and we'll make it inject into every single process. And when we also hook POSIX spawn, we can control the environment variables of the child process. And we can basically add DLLD insert libraries here to make the child process also load our hook. Unfortunately, under normal circumstances, the dynamic linker DLLD will simply ignore this DLLD insert libraries variable. So we need to find a way to make it work. So the reason why it will ignore it is something called amphiflex. So DLLD will actually call out to the kernel to get these amphiflex, and these amphiflex dictate what environment variables are allowed. And the DLLD insert libraries variable specifically is only allowed if the process has the get task allow entitlement. In practice, this is only done when you want to debug an app, then you would give it this entitlement. But obviously, that's not really a thing that we can do, so we need to figure out a way to bypass this requirement without the entitlement. And to do this, we can simply statically patch DLLD. We find the getAmphi method, and we simply return it replace it with a return 0xdf. 0xdf in this case means allow all environment variables. So now we have a statically patched DLLD, but we still need to figure out how to make the system actually use it. And for that, we can, so normally the stock DLLD is inside user_lib. This is a read-only path, so we cannot just replace it. Also, if we could replace it, that's very dangerous and could cause boot loops if we don't have persistence. So the idea is to just modify this path just for the current boot. So we can simply mount on top of it, or mount a different path on top of it, and then replace the file in that path. And that way, we can essentially make this DLLD binary inject into every newly spawned process. Although it is important to note that we need to actually inject the hash of this DLLD file also to trust cache for this to work. So in practice, we will use a bind mount for this. So we will essentially copy the contents of user_lib to some writable location. And then we will replace the DLLD in that folder with a statically patched DLLD, and then mount the writable folder on top of the existing user_lib. And normally the sandbox rejects this, like it doesn't allow us to mount on top of this path. So, but we have PPL read-write already, so we can simply temporarily borrow the kernel user credential and replace our own process's user credential with it, then do the mount, which will work because the system thinks we are the kernel. And then the DLLD binary, or the bind mount has been applied. And after this, any newly spawned process will use our patch DLLD, which will allow DLLD library, insert libraries. So essentially, we have bypassed code signing by simply injecting into the entire system, intercepting every single POSIX spawn call, adding the binary to trust cache, then calling the original implementation. This is done by launchd. Launchd uses PPL read-write to actually perform our stuff. And yeah, this is it. Thanks. I will quickly show a demonstration also. All right. Here we have totally not my daily driver phone. This is on iOS 15, but the same stuff works on iOS 16 as well. And so using the techniques I've shown, I've also written a full jailbreak. And so I can quickly demonstrate this. Okay, it's in German, that's a bit bad, but yeah. So it will exploit the kernel, it will apply the code signing bypass, and then it will reboot the user space into jailbroken iOS, which is what it's doing right now. So this will essentially restart launchd and have the system-wide hook applied everywhere. And then code signing is bypassed, and we can, wait 1 second, just keep focused. And we essentially, for example, can run a terminal. Yeah, that's it. So at this point, we have full code execution, and the jailbreak is complete. That's it. Thanks.
Thank you very much, Lars. That is a very mind-blowing sessions that we had.